This is the second mini-lecture for section 13.1. We're going to continue our discussion of representing numerical data. At the end of the last mini-lecture, we talked about the histogram for this data set that we'd begun that lecture with. So now let's turn this data into a line graph. Okay, so I'm going to use the same intervals, same data set, same intervals. And I'm going to begin the graph just like we did the histogram, because it's actually kind of based on the histogram. So we have interval 1, 2, 3, and 4. Okay, the data needs to go up to 13, or the vertical axis needs to go up to 13. And here's how to think about the line graph. I'm going to very lightly sketch a histogram here, the same one we just drew. That's not part of the line graph. I just want you to see how they're related. So I'm just going to very lightly sketch that in. Okay, because like I said a moment ago, the line graph is kind of based on the histogram. It's a different way of showing the same material. Okay, so you can see kind of the ghostly outline of our histogram here. So the way to produce the line graph is to just put a vertex or a dot at the middle of the top of each of those rectangles. And I like to also put a dot to the left and to the right in these empty spaces. Okay, and then I just connect the dots. And this is the line graph. So it's really showing exactly the same thing that the histogram did, but it sort of smooths out the data and maybe for some things kind of gives you a better idea of the shape of the data than the histogram. Okay, so there's our histogram for our data set. And notice that if I take these little imaginary bars that I had for my histogram, and I imagine using the lines that I just drew to chop off the corners of the rectangles, like maybe this rectangle. I'll shade it in really lightly because so it's not part of the graph. I just want to show you the geometry of it. So if I take that little piece that I chopped off and imagine flipping it around upside down, it would fit in right here to kind of fill in that gap. And I could imagine doing that for each of those corners. And so what I'm doing is producing a graph that has the same area as the histogram. Again, it still satisfies this property that I mentioned for the histogram, that if you regard each interval as being 1 unit wide, the area under the line graph is equal to 24, which is the size of the data set. And if all I had were this chart, and I wanted to estimate how many people scored between X and Y on the horizontal axis, 69 and 77, or just whatever numbers I wanted to make up, I could figure out the area underneath that graph for that interval. It would be some number between 0 and 24, and that would be an estimate for the number of scores on that interval. Okay, so the histogram and the line graph are both graphs that turn the data into area. And that's an important thing we'll return to in a couple of sections. Okay, so the other graphs we have to talk about are used for categorical data. So, we've been talking about things like test scores. Categorical data might be how many students I have at each site, for instance. I've got 25 students, and there's 12 in Eagle Pass, 9 in Del Rio, 4 in Uvalde. So that's categorical data because there's no, Eagle Pass and Del Rio and Uvalde are not numbers. They're names. They're names of towns. So it's not like there's a predetermined order that these towns have to go in. I could list them. I could list the populations from least to greatest, or greatest to least, or I could use alphabetical order, or whatever I wanted to. It looks like, as given, these are going least to greatest, or greatest to least. But to do the picture, let's just do alphabetical order, just because, like I said, it doesn't really matter. And we don't have the same relationship between area and the data here because there's just, well, it's not numerical data. The area doesn't really have any significance. So, I can use separate bars if I want to. Del Rio, Eagle Pass, and Uvalde. Del Rio is 9. So here's a bar that's 9 units high. Eagle Pass, it's 12. And Uvalde is 4. And there's our bar graph. Okay, so, I'm sure everyone knows how to do that. Another way of representing categorical data is to draw a pie chart. Okay, ordinarily, of course, you just use a computer or something for this, but it's good to do it by hand at least once or twice to make sure you really understand what role the geometry is playing. So we'll use the same data for the pie chart. We have Del Rio, which is 9 students, but it's 9 out of 25 total. So I'm going to write that fraction, because the pie chart really, it doesn't display the total amounts per se, it displays the fractions. So Del Rio is 9/25 of the class. If I write this as a decimal, let's see, multiply top and bottom by 4, or whatever I want to do. I get 0.36. So that's going to be 36%. Eagle Pass, it's 12/25, which is 0.48, which is 48%. You just use a calculator if you need to. Uvalde is 4/25, which is 0.16, which is 16%. So these are the fractions of the amounts. Now, in my pie chart, I need a circle. Try to draw a really good circle if you can. I used to use a compass and a protractor to do this. I'm not doing that now because I feel like it puts the emphasis on the wrong thing. You want to try to be as exact as you can, but the main thing is to just understand the role played by everything. Okay, so how to use the circle. Let's put a dot in the middle. There's the center. And, each of these categories gets a wedge of the circle whose angle corresponds to the percent represented by that category. So the fraction of the 360 that the angle represents should be equal to the fraction of the population represented by that category. So 36%, for instance. If I do 0.36 times 360 degrees, I get 129.6 degrees. So if I do 0.36 times 360 degrees, I get 129.6 degrees. Okay, and this is just to help me draw Del Rio on here. Okay, Eagle Pass. We have 0.48 times 360 degrees. $172.8 degrees. And then Uvalde, we've got 0.16 times 360 degrees. $230.4 degrees. That's not right. 57.6. Sorry, I don't know how I got that. 57.6 degrees. And these all should add up to approximately 360. Sometimes they might not because you rounded. And these are just guides for drawing the pie chart. Okay, you're not going to actually write them on the pie chart. Just if you were using a protractor or something, you could use this to draw it accurately. Okay, so Del Rio needs to be 100, about 130 degrees, which is maybe something like that. And then, so this is Del Rio, 36%. Okay, Eagle Pass is a little bit less than a half. So something like this maybe. It's very close to a half, but not quite. So this is Eagle Pass, 48%. And then what's left over is Uvalde, of course, which is 16%. Okay, so there's our pie chart. Okay, the textbook also discusses pictographs, which uses small figures or icons to represent data and trends. I would recommend looking at the examples that the textbook uses. Look carefully at all the textbook examples. They've got some good examples of graphs that are misleading. And this comes up a lot in statistics. There's an old saying about statistics, which is that there are three kinds of falsehoods: lies, damned lies, and statistics. And there's a lot of truth to that because you can, while statistics is necessary to really understand any complex situation, you can use statistical representations to mislead people that don't know the details of what you're trying to represent. And so it's really important for citizens to have a good understanding of statistics.